All right. So this is probably going to be one of my most favorite sections. We're going to be talking about work done by a variable force. So if the force is a variable force with f of x being the capital F of x being the force, the variable force object is being inserted on an object moving along the x-axis, then we say that the work done is the integral of the force over the distance or over the displacement. Okay. So we're going to illustrate this with probably two examples for now. Yeah, okay. So the first one is imagine a spring has a natural length of 1 meter. A force of 24 newtons holds the spring stretched at 1.8 meters. Okay, and so the problem kind of walks you through some ideas here. The main idea here is to find K, given the information provided, and then we'll look at how much work it would require to stretch it to 2 meters beyond its natural force, and then determine what the stretch in the spring is if we have a 45 Newton force on the string. Uh, so I like to just draw a picture to kind of make sense of these to start off with. Maybe I'm just I don't know, but I do like to draw a picture to kind of get the idea of what's going on here. So I always imagine just a force. Um, for all these problems, I'm always imagining a block on a spring like so. And so I'm going to take the origin of my coordinate system, and this is a real common practice, to be 0 when the spring is at rest in this direction. Okay. It said that the spring's natural resting length is 1 meter. So this distance here is L, that is equal to 1 meter. That's just the length of the spring, but I'm going to call 1 meter equal to 0 for our first. In other words, when there's no force acting on the spring, then the resistance or the distance is going to be 0 here. Okay, so then I'm going to imagine a force F being applied to it this way, like pulling the spring out. Okay, and so the picture that we currently have is that this has been stretched out some distance, and so here, if you will, if we can imagine, this is where my new block is. Okay, and so for us, this is going to be my delta x, okay? My change in the position of this. Okay, and so the force that's governing this is known as Hooke's law. Okay? And it says that f of x is equal to uh, k, which is the spring restoring force, force constant. Okay? And then x is the displacement from x is distance from equilibrium, where we define equilibrium to be 0 here. Okay, so that's the situation here, and so the with the problem, someone like we're pulling the spring out, and right now in the original problem it says that it's been pulled out a distance of 1.8 meters, and it has a force of 24 newtons on it. Okay, so what that means for us, since the distance and of the force and the direction of the force are perpendicular, it means all the direction is in the force. So for A actually is just a straightforward calculation. What it's saying is that a 24 Newton force, that's the F, is equal to K, the spring constant, this is what we're looking for, times the delta X. Okay. And then the delta X here, this is the one that's maybe a little bit tricky. Since the original spring has a length of 1, then the displacement from that is going to actually not be the 1, but actually the 1.8. So this is going to be 1 minus, or you can say 1.8 minus 1, or translating it to our system here, what I call delta x. This distance for this part of the problem is equal to that 0.8. Okay. So just depending on how you want to calculate that. All right. So then, in other words, the work that's going into this 24 Newton force doesn't start up taking effect until you get past that first meter. Okay. So you get 0.0, or sorry, 0.8. Okay. And so dividing both sides by 0.8. What is that? 24 by 0.8. Within 3. Actually, it wasn't even 30. So K is equal to 30. Now, we want newtons out of this calculation, and we just divided by 0.8 meters. So K is in Newton meters as the units. Okay. All right. So our constant, our strain force constant. Yeah, I think that's right. Is 30 newtons per meter. Okay. So we'll use that then in the next part of the problem. So the second part of the problem said how much work goes into stretching a spring 2 meters beyond its length. Okay, so we know our force that's here. We just found what the K was. It's a variable force, so it's going to always be adding, so it's going to be changing. It's not a constant force. So we're going to have to integrate, and we're going to go 2 meters beyond. So our limits of integration will be from 0 to 2. Okay, so for B, the work done to move this thing from 0 to 2 meters is going to be 30 Newton meters. This is the K times X. X is in meters, dx. Integrating this, we're going to have 30 Newton meters. This is a constant integral from 0 to 2 of x dx. Okay, so add 1 divided by it, so we get 15 Newton meters. The 15 coming from 30, this is going to get us an x squared divided by 2. Half of 30 is 15. X squared evaluated from 0 to 4. Sorry, not 4, 0 to 2. And then these are going to be in meters. So we're going to get out, this is going to be 15 Newton per meter. And then I have 2 meters squared minus 0 meters squared. Just being thorough here, so obviously that doesn't count. This is going to be 4. 4 times 15 is going to be 60. The meter squared, one of the meter squared is going to cancel with a meter here. And so we're going to get 60 Newton meters, which is exactly what we hope to get because this is 60 joules. So the work done then, the work done is going to take 60 joules to move the spring 2 meters beyond its resting position. Okay. And then the last question said, how far will 45 Newton meter, or how far will 45 Newton force stretch the spring? Okay. So we have a force of, let's see, we want to know x. We have a force equal to 45 newtons. And we want to know with a 30 Newton meter force what the displacement for x would be. Okay, so just dividing both sides by 45 divided by 30. You have newtons, and then you have Newton over meter, which produces meters, which is what we want. 15 will go into both of these 3 times and 2 times respectively, so 3/2 meters. Next, so it will be the displacement will be 1.5 meters. So x is going to be 1.5 meters. Will be the displacement for the. All right. That was pretty straightforward. Good little problem with springs and Hooke's law and the variable force in one dimension. All right. I hope that was helpful, and I'll see you in the next video.